The moment-generating function of a random variable x is defined as m sub x of t, the expected value of e to the tx. For x following the normal distribution with mean mu and variance sigma squared, we write this as the integral of e to the tx times the Gaussian density. This integral has a beautiful closed form. We will derive it by completing the square in the exponent. The result encodes every moment of the distribution in a single exponential and reveals why sums of independent Gaussians are always Gaussian. The key insight is to examine the exponent of the combined exponential. Inside the integral we have e to the tx times e to the negative x minus mu squared over 2 sigma squared. Combining exponents gives tx minus x minus mu squared over 2 sigma squared. The trick: complete the square in x, treating t as a fixed parameter. The combined exponent rearranges into a perfect square in x, plus a constant that depends only on t. That constant, mu t plus sigma squared t squared over 2, becomes the entire exponent in our final answer. Step by step, combine the two exponents over the common denominator 2 sigma squared. Expand the numerator x squared minus 2 mu x plus mu squared minus 2 sigma squared tx. Group the x squared and linear x terms. The coefficient of x is 2 times mu plus sigma squared t. Factor out negative 1 over 2 sigma squared and rewrite the bracket, ready for the perfect square. Complete the square. Add and subtract mu plus sigma squared t, all squared, inside the bracket. The perfect square x minus mu plus sigma squared t emerges. The leftover is mu plus sigma squared t squared minus mu squared, which simplifies to 2 mu sigma squared t plus sigma to the fourth t squared. Divide by 2 sigma squared. The constant is exactly mu t plus sigma squared t squared over 2. Watch. As t varies, this constant traces a parabola, and that parabola is the exponent in the moment-generating function. This is the critical step, the one where most students lose the thread. After factoring out the constant exponential e to the quantity mu t plus sigma squared t squared over 2, the remaining integral has exponent negative x minus mu plus sigma squared t, all squared, over 2 sigma squared. Look carefully at that exponent. It is the exponent of a normal distribution centered at mu plus sigma squared t. Watch as t changes. The bell curve shifts left and right, but its total area stays locked at exactly 1. Any normal probability density integrates to 1 by definition. So the entire remaining integral equals 1, and we are done. The moment-generating function of the Gaussian is m sub x of t equals e to the quantity mu t plus sigma squared t squared over 2. Verification: the first derivative at t equals 0 gives exactly mu, confirming the mean. The second derivative at 0 is mu squared plus sigma squared, from which variance equals sigma squared. Every moment is encoded in this single exponential. The curve shown as convex equals 1 at t equals 0 and grows in both directions, as every moment-generating function must. Here is why this result matters beyond this one derivation. If x and y are independent Gaussians, the MGF of their sum is the product of the individual MGFs, multiplying the two exponentials and collecting terms. The mean of the sum is mu 1 plus mu 2, and the variance of the sum is sigma 1 squared plus sigma 2 squared. That is the MGF of a Gaussian with those combined parameters. Sums of independent Gaussians are Gaussian. The MGF proves this in one line. Watch as the combined variance grows. The bell broadens, but stays Gaussian. What if x and y are not independent?